Hello, this is Mrs. Huntley. We are in Module 4, Linear Relationships. You're in your supplemental packet, but that has this on the front. I would like you to turn to student handout number 7, which is titled Multiple Representations. And at the top, you can add the essential question. Linear relationships can be represented as an equation, a graph, a table, and in words. How can I represent a relationship through all the different modes? So the directions tell us we're going to practice representing linear relationships in multiple ways with the following examples. Use the representation that's given to help you fill in the others. So in the first one, it's like a traditional story problem. They're giving us the verbal description. They're asking us to write the equation, fill out the table, and then graph the information. So a baby giraffe measures 6 feet tall when it's born. So on the day that it's born, it's 0 months old. It's 6 feet tall. It grows an average of half a foot each month. So we don't know how many months we're going to be talking about, but we're going to be talking about various months and trying to figure out the total height. So we're going to say y is our total height. X is our number of months. So when I'm writing the equation, y, my total height, is going to be equal to the amount that they're growing, 1/2, times the number of months, plus the initial value. The initial value, he was 6 feet tall when he was born, or she was born, okay? And we're growing a half a foot each month. Does that make sense? So, if I'm using the process, I'm going to plug in my values, my months, to figure out my height. So I'll take 1/2 times 0 plus 6. Well, 1/2 times 0 is going to be 0, so it's going to be 6 feet tall. At birth, he's 6 feet tall. 1/2 of 1 plus 6. Well, half of 1 is a half, so he's going to be, at 1 month old, he'll be about 6.5 or 6.5 feet. Go ahead and pause the video and fill in the rest of the values. So we'd have 1/2 times 2 plus 6 for the next one. Half of 2 is 1 plus 6 is going to be 7. You might be seeing a pattern. Go ahead, like I said, and pause the video. See if you can get the rest filled in. Okay. Hopefully your table looks like my table, and if it doesn't, go ahead and make the correction. Now you could have had the y equals out in front if you wanted to. That would probably be more correct, but I figured since we had our y over here, we were good. Now on our graph, we should title the graph. This is our growth of our giraffe. Oops, only one R. Spelling is not my forte. G-I-R-A-F-F-E, giraffe. Okay, my X is my number of months. And my Y is the height. So at 0, okay, so let's just label this up. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can go up to 10 months on this particular graph. And then my height, I'll go by ones here too. That's probably the easiest. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at birth, he was 6 feet tall. So my y-intercept is at 6. Now at 1 month, he was 6.5. So I can kind of eyeball and go, between 6 and 7 and make a dot there. Or I can stick to my whole numbers. And I could just say at 2, he was 7. Let's see, at 4, I'm going to come down here, he was 8. And at 6, he was 9. And then when I draw my line, it's going to catch all those other values. See what I mean? So now if I take this up, that's right at about at a half. At 3, I'm writing about a half. At 5, I'm right about a half. So I catch all those other values even though I didn't graph them intentionally. I tend to use that as a strategy when I can't figure out exactly where those fractions are going to fall, is I just figure out which ones are going to be integer coordinates. So number 1 in the questions below, it says, how did you find your ordered pairs to create your graph? Well, we kind of took them from our table here. We could have taken them from our equation as well, because our y-intercept was 6, and then I was going up 1, and over 2, up 1 and over 2 each time I was graphing it. So that would have worked as well, but we did take them from our table. So I'm just going to say we took them from the table. What is the slope of the graph, and what does it represent? The slope of the graph is 1/2, and it represents the growth of the giraffe each month. Oops. So 1/2, and it represents the growth of the giraffe each month. What is the y-intercept of the graph, and what does it represent? The y-intercept of the graph is 6, and that represents the initial value, or the height of the giraffe when it was born. It was a value before we started multiplying anything. So at 0, at 0 months old, it was 6 feet tall. Okay, it represents the height of the giraffe before it was even a day old. What does the ordered pair 9, 10 and a half mean? So let's come up here and look at 9. And it's not on our graph. It would be up here. What would it represent if I had it on our graph? Well, our x's were the months. The y's are the total height, right? So it represents at 9 months old, the giraffe will be about 10.5 feet tall. If the giraffe is 12 feet tall, how many months old is it? Okay, so we can use the equation, and we can say at 12, I need a pen. At 12 months, so when y is 12, what is x? So now we just have to go about solving for x using our properties of equality. Okay, we could also use our table. If I had done my graph differently to where we could actually see these values, and I could have, like if I had gone by 2s on the months instead of going by 1s, perhaps I could figure it out from the graph. But right now I'm just going to use the equation. Or I could go back to the table, I suppose, as well. So I'm going to try to solve for x here. I need to get the x all by itself, so I'm going to subtract 6 from both sides of the equation. So 1/2 x equals 6. Now I'm going to divide by a half, which is the same thing as multiplying by 2. So x is going to equal 12. So when he's 12 feet tall, he's going to be 12 months old. Okay. If this isn't exactly making sense to you, it's probably because you're a little bit weak on the properties of equality. And when you're dividing by a fraction, you're actually multiplying by the reciprocal. So those are skills that perhaps are a little bit weak. And I will explain it more in class tomorrow. Let's move on to the next example. Okay. Use the representations given below to fill in the missing representations. Okay, so I have an equation here. I don't know exactly what it means yet. Y equals 1.5x plus 12. And then I've got a table that I've got toppings, process, and cost of pizza. This must mean that this information has something to do with the pizza parlor. Oh, wait, look at my graph here. It says Joey's Pizza Parlor cost, and my X is the number of toppings, and my Y is going to be the total cost of the pizza. So my verbal description could be something like, at Joey's Pizza Parlor, a large pizza costs $12, because I see that's my beginning value, plus $1.50 for each topping, because I'm multiplying this value by the number of toppings to get the total cost. So I'm starting here at 12. That's my initial value, my beginning value. So before I add any toppings, my pizza is going to cost 12 bucks. So I'm going to use the process. Y, or total value. Come on. Y equals 1.5 times 0 plus 12. So my cost of my pizza is going to be 12. Y equals 1.5 times 1 plus 12. So that's going to be $13.50. Go ahead and pause the video and fill out the rest. Okay, there you go. So with one topping, the cost of the pizza is $12. $13.50. With two toppings, it'd be $15. Three toppings, $16.50. Notice that this is going up by our rate of change. So there's plus 150 each time. That's what your rate of change means, is your Y is going up by that rate each time. So when I'm graphing it, 0 toppings, $12. That's my initial value. One topping is $13.50. Now here's a situation where I don't know where $13.50 is going to fall, guys, because this is going up by 2's on my Y-axis. So I'm going to stick with just putting in my values that are actually going to be on my graph. So the next whole number that I have that's on my Y is 18. So here's an 18 down here. I'm going to highlight it for you so you know where I'm looking. You don't have to do it this way either by any means, but here's 18 and 4, and here's 18 up here. So I'm going to come over here and go over to 4 toppings and follow it up to 18. And I know that's another point that's going to show up. So I can take my line now. I've got 2 points that are on my graph. I can take my line and draw a line through it. And I'm relatively sure that all of these are going to fall on the graph. So let's take a look. At 2, I said it was going to be about 15. So let's follow 2 up and see. Oh, look, I'm above 14, but not quite the halfway point. Does that make sense? And it would have been really hard for me to eyeball this without knowing that I had another integer coordinate. I could have eyeballed it, no problem, but I just chose to do it a different way. So 1, let's see, does 1 look like it's $13.50? Yeah, it does, doesn't it? So that's how I choose to do my graphs when I have data like this. Okay, the last one. I don't have an equation. I don't have a verbal description. I've got a table, and I've got my x's and y y's, but I don't know what's happening to my x's and my y's. And then I've got, let's see, this is titled Woodbury Watermelon Patch, number of watermelons and the weight of the watermelons. So as I'm going up 5 watermelons, my weight is going up 3 pounds, 6 pounds, 9 pounds. Okay, so I know that it has something to do with pounds and watermelons. So watermelons are my x, pounds are my y. I can take my y divided by my x. So 6 divided by 5. Let's see what I get with that. 6 divided by 5 gives me 1.2. Okay, now I wouldn't necessarily want to keep that, but what I have to do is check to see if this is proportional, meaning at 0 watermelons, I'll have 0 pounds, or if it's going to be a non-proportional relationship. So I need to check some other ratios here. So 12 divided by 10, let's see what I get there. 12 divided by 10 is 1.2. Okay, good. I'm still proportional. 18 divided by 15, 1.2. I'm just checking all of them real quick. 24 divided by 20, yep, 1.2. And then, of course, 30 divided by 25. I'm taking my y, dividing it by my x. I get 1.2. That means this is a proportional relationship. When I have 0 watermelons, it's 0 pounds. Now, that kind of makes sense, but I needed to be sure of it before I went any further to make sure that, you know, at 0 watermelons, there wasn't like 1 pound. Maybe the plant had some weight or something like that. So how would I write this equation? My total weight equals 1.2 times my x, or I could say y equals 6/5 of my x. Now, what does this mean in the context of the problem? See, I'm kind of going about this one backwards, and this one is kind of the most confusing because I was assuming that it was going to be money for the watermelons, not the pounds. So this one actually confused me too. What does it mean? At Woodbury Watermelon Patch, watermelons weigh 1.2 pounds or 6/5 pounds per watermelon. So each watermelon weighs 1.2 pounds. So if I want my total weight, it depends on the number of watermelons. So let's go ahead and graph this information. At 5 watermelons, I've got 6 pounds. At 10 watermelons, I've got 12 pounds. These are all integer coordinates that are going to be on here. At 18, ooh, 18's not on here. Oh, 15 is on. Okay, I'm spacing out. Sorry, 15 watermelons is 18 pounds. 20 watermelons, 24 pounds. 25 is 30. And again, I could have just graphed a few of them and then drawn my line to get the rest of them in there because they're all going to fall on the line. Whoopsie. On my line. Okay? So summarizing today's lesson, there are many ways that I can represent my linear relationships in words, with a verbal description, with an equation, with a table, and with a graph. I can flip between any one of these. I can match them up. These are all representing the same thing. It's just different representations and different ways of showing the information. Sometimes it's really nice to be able to look at a graph and go, oh, I can estimate how many 35 watermelon, if this was a taller graph, I could estimate how many 35 watermelons would weigh based on just where it's going to fall on the graph without going through and doing it in the equation. So that's what these are the 4 different representations of linear relationships. Again, mark any questions that you might have, bring them to class with you, and we're going to be doing a matching activity in class to hopefully solidify this learning for you. Have a great week. I'll see you soon.